Hi class. So today's lab or this week's lab is alum from used aluminum. This is a lab that we actually do at Citrus. I do it with my class. Um, so I'm going to give you the way that I do this lab in my class and not the way that LabFlow has it set up. I understand what they're trying to do, but I'm not exactly thrilled with how they presented this lab. So this lab may seem very difficult or complicated. Not the way I'm going to show you how to do it. Okay, so aluminum synthesis. Alums are widely used in tons of applications with deodorants, water purification. You get the idea. It's in everything. I honestly had never heard of alum until I had to present it for my class in lab. So this is a good lab that if we had been in person, if you ever thought of being a chemist, this is a good lab to get an idea. There's multiple steps with dangerous stuff that you have to pay attention to, and you get to go through steps and see your product at the end from when you started with just an aluminum can. It is purified through a process of recrystallization, which means that we're going to end up with a precipitate. But by this point, it should only be the alum that will connect together all the molecules, compounds, and push out all the impurities. So this is a purifying process as well as producing a precipitate. From there, we will determine a percent yield. And if you're a chemist, I'm a chemist, I still work in a lab, and every reaction I ever did, I had to give weekly meetings about how what I did for that week, and they're all reactions, and everybody the first thing they want to know is percent yield. How successful was this reaction? So that's what you're doing here. This is a aluminum reactant problem, and we're also going to determine theoretical, and then we're going to produce a percent yield. So your PDF shows you the net ionic equation, which you can use, but this is the full equation, and this is the one that I show for my class. This is called potassium aluminum sulfite dodecahydrate. The word hydrate here, that means that you see this dot and 12 waters, that's 12. 12 is dodeca. And hydrate means water. So this is a compound that without that, it would just be potassium aluminum sulfate. So it would just be this part. The fact that there's a dot and it's called dodecahydrate means there's 12 waters attached. The 12 waters that are attached are actually attached in the lattice structure of the compound. They are trapped in there. They are not just hanging around because of attractions, electrostatic polarity, anything. They're actually trapped in the structure. So when you have to determine the formula weight, you have to account for those 12 waters and add that as well to the whole formula unit. So this is the whole compound that I'm going to show you. And at the end, you produce hydrogen gas and you produce your compound. This is just here explaining what I just told you with the hydrate. Okay, so the purpose of this lab is to produce alum from something that's been used. So if we had been in person, each of you would have had an aluminum can, you would have cut it up, you would have taken some steel wool, and you would have scraped the inside and the outside as well as possible. I'm telling you, this is a fun lab. If you don't, you leave any bit of coating on it, the reactions take a lot longer, you have a lot more problems, and your yield will probably not be as well. Because when you have impurities, sometimes those impurities make side reactions. So the first thing I always tell my class is if you're going to do something in chemistry, do it right the first time so that you do not have to spend endless time watching your reaction while everybody else has moved on. So that's not the time to be lazy or just kind of a little not paying attention. Do it right from the beginning, and everything usually goes well. So you would scrape off the coatings that are on the soda can on the inside, which is a coating to, there's just a coating in it. I'm not going to go into it too much since we're not really doing this in person. And the paint that's on the outside. So here are the reactions. I'm not a big fan of how LabFlow set this up, and I think I mentioned that already, but I'm going to go through this briefly with you. There's multiple steps, and you would have did all these steps. There's a reaction of aluminum with the potassium hydroxide. So aluminum is the limiting reactant. When that one ends, that's when the reaction stops. So here in this case, you would actually, instead of having, we would do a little bit more excess, probably 10% more of excess of potassium hydroxide to ensure that we use up all the aluminum in this reaction. So we're dissolving the aluminum when it reacts with potassium hydroxide. Then the next step is you're going to add a certain amount of sulfuric acid, and it's going to cause our product for the second reaction to create a solid. Now the weird thing here is that in the third step, we're going to even add more sulfuric acid to cause it to dissolve. Now the fourth step is we're going to cool it, and when you cool it, that will create a solid. Now the problem is if you add too much sulfuric acid, that will cause problems or delay to creating the sulfuric acid. And usually what you do is you have a glass rod, and it's really strange, I know, but you get a glass rod and you scratch the glass inside. You're not really making a dent, you're just kind of scratching, causing friction, and that friction usually causes the precipitate to form. And if you're going to Chem 111 and you are in person, this would be one of the first labs you did if it wasn't on lab flow. I also teach Chem 111 lab, so I know this. So here's the overall net ionic equation that's at the bottom. All right, so I'm going to go through the procedures because lab flow did not really produce procedures here. And I'm not a big fan of how I think this lab could have been rewritten differently. I know what they're trying to do. They're trying to make you compare costs analysis. We'll cover all that later. So in this lab, my sample, I'm giving you what would have probably been given you in the procedures had they given you correct procedures. So you're going to weigh out 1.25 grams. For the first reaction, I know I did a poor job here, but each of these lines means it's separate for those part of the reaction. So aluminum is a limiting reaction. So potassium hydroxide is going to be in excess, but we want to make sure. So if we are doing just a reaction of matching the moles, it's going to be 2.6 grams of potassium hydroxide is what you need. But we want to make sure that the aluminum is completely reacted. So we're going to use 10% more, and that's going to be 2.86 grams. And the water, you would use 2.5 mils. Then we're going to heat this up gently because that speeds up the reaction. Now when we get to the second step, we're going to use, we have the product from the first step, and then we're going to add sulfuric acid. We're going to add 2.57 mils of sulfuric acid for the second step. We get to the third step, we're going to add 7.72 mils of sulfuric acid. And again, if you would add more than this, you would probably have a hard time of your precipitate forming. So you want to add just enough that it would form, and if not, you would have to scratch it. And then by this point, when we get to step 4, we should have a precipitate, which is what we're going to figure out the theoretical yield for. So this is the steps with the amounts of what we would use. Okay, so once, oh, this moved again. Sorry, I apologize. I fixed this, and it moved, and I didn't catch it. So this is right here. Imagine it's directly underneath. This is a limiting reactant, which means that you're going to have a limiting reactant, you're going to have an excess, and you're going to calculate the theoretical. The theoretical is what you have to, okay, so let me explain this a different way. When you're doing the limiting reactant and you have to get to percent yield, you will always be given the actual value. So it'll be in a word problem or something telling you mass that was, produced. It's not actually saying it's the actual, but that's what was completed in lab, and it's given to you. What you always have to do is calculate the theoretical. The theoretical is different because actual is what's done in lab. Actual is never matches theoretical. Trust me, I'm an organic chemist. It never matches. Theoretical is what is done on paper under pristine conditions, if no human air, no air at all, no impurities, the max amount that can be produced on paper. But it never really exists because nobody ever gets to that point. And it should always be larger than your actual. So if it is not, there's an impurity that's causing your values to be wrong here. So this is what we're going to do. We're going to calculate the theoretical. And with that theoretical, you're going to be given an actual on lab flow in the data report part. And then you're going to determine the percent yield. So this is mine. This numbers do not match what the amounts that are given on lab flow, but you're going to go through the same process. So I'm going to use this equation, and I'm going to say that my mass for me, from my experiment, is 0.475 grams. It's not even close to what you're given on lab flow, but it doesn't matter. You're going to follow the same steps, and you're going to find that this lab is one of the easiest labs that you have done this whole semester because I'm removing all the problems to it. You're going to start with this, and now you're going to do stoichiometric stoichiometry. You're going to do dimensional analysis. You can break these up into different steps. I do not. I do them all in one step. So let's get from 0.47 grams. Here is the molar mass of aluminum. So we set up the first part. And now we have to do the ratios from the equation. I have 2 moles of aluminum. I also have 2 moles of alum. So that's where the 2 and 2 come from on here. Then, now that I'm at alum, I need the molar mass for alum. I have the molar mass. And from 0.75 grams of aluminum for my reaction, I produced 8.35, and this is usually where the sig figs, it's indicating an extra sig fig. So you never round to the very end, and I usually keep all my sig figs till the end. More than past my sig figs, so that I don't round to the very, very end. Okay, so I produced, my theoretical now is 8.35 grams. This means that on paper, perfect conditions, this is the max amount I would have produced. Now the lab amount is 2.930. So this is what was given to me that was produced in the lab. You can see it's considerably different. And in most cases, and probably yours, it won't be this huge of a difference. But this is numbers that I picked because it's just I picked. So here's a 2.930, and this is how the calculation should actually look on here. I'm going to set up with 2.930 grams of alum, and my theoretical is 83.51. I keep everything to the end, and then I reduce it to the correct sig figs. Is 35.1%. So follow the rules that you follow, because I realize lab flow sometimes gives this amount in this sig figs and this amount. Follow your rules, understanding sig figs. So this overall experiment produced a 35.1% yield. This is not a difficult lab. I'm showing you the easiest way. So the 2 things that you need to do for this lab, you're actually only going to have 2 calculations, believe it or not. I've cut out everything else. You're going to have to determine the theoretical, and you're going to have to determine the percent yield. You're going to be given a whole bunch of information. Pick out the parts that I'm telling you to use, which is the mass, and then go through the exact same steps, and you're going to be able to pull out your theoretical. The rest of it, LabFlow, I believe, wants you to break this down step by step by step and do stoichiometry through every step using different substances. And I do this lab in person. We don't do that, and I'm not going to have you guys do that. So if you do it my way, I did use numbers that LabFlow, I go through every lab on LabFlow. I did this lab myself, my way, and I was fine. I got everything right. Now, there's different uploads. I was going to have you upload certain sections and then not upload other sections, and I just decided that I'm not going to take any uploads on this. You're going to get credit for that. Don't worry about it. Because there's a few uploads. They want you to do a cost analysis by looking up Fisher. These are companies that I work with in my lab to determine amounts. This is not a report that I'm asking for cost analysis. You do not have to do any of that for me. This is, I want this straight to the point. I don't think chemistry has to be any more difficult than it already is, and I don't like this lab. I think it could have been done better. So I'm going to give it to you the way that I do in my lab. So no uploads. Ignore the uploads. Don't panic. I'm not taking uploads for this. I'm telling you right now. That's it. This is a very easy lab. I know it seems more complicated, but I've removed a lot of that stuff. Excuse me. Read your PDF and watch the video on filtration. I did not answer everything because there are answers to your quizzes in the filtration video, and there's answers in your PDF to the quizzes, but I've covered everything I can to help you as much as possible. Okay, and that's